I'm going to go as slowly as I can because of that. So hopefully you can catch it up. Now, what do we have? We have a bat. That is traveling or flying at a circle. Okay. So this is a little bit involved problem. There's going to be lots and lots of parts in it. So my suggestion is that try to follow it as much as you can. The reason being, although the questions that you will have in the exam may not be as hard as this, the point is that parts of this might come up as problems in the exam. So let's try to focus and let's try to understand what's going on. Okay? So first off, it's given to us the lifting force of this bat is less than or equal to this number. 0.18 Newton. Okay, so lifting force is what makes the bat stay aloft. In other words, makes it fly, right? So, what is this meaning? What is the meaning of it? Now I use something else, v squared. And I'm going to do one other thing here. I'm going to place c here because it will be easier for me to write it with a constant rather than writing this whole thing. So what is the meaning of this? Let's try to understand. Means that lifting force is related to velocity. So in other words, by increasing velocity, you can increase the lifting force. However, it doesn't necessarily mean that if something would be traveling really fast, that would necessarily mean that it will have a higher lifting force. For example, now if you think about the lifting force is where you use your wings. In this case, the bat is using its wings and it's moving forward with a velocity v, and using the air around it and the wings it's creating a lifting force upward. Okay? So now the question is, if I go at a particular velocity, am I always going to get a lifting force? As an example, think about a hawk trying to catch a mouse on the ground. So when the hawk comes down really, really fast, what do you get? It increases the velocity as it comes down, but does it have a lifting force that goes up with it? If it has a lifting force, would it come down? No, because then it should go up. So the only forces that balances or lift a bat, so this is my bat, of course it's like Picasso's pictures, right? But hey, this is my bat, so this is my lifting force. Okay? So the bat is flying outwards. So as it's flying outward, it gets this lifting force that forces it to move up. Now it also has a weight acting down. Now if the weight is bigger than the lifting force, what's going to happen to the bat? It's going to come down if it's controlled. If not, it's going to crash down, right? So on the other hand, if the lifting force is higher than the weight, it's going to go up, right? So flying is a delicate balance between these two, especially controlled flying, right? So Now my point is this, in the case of the hole coming down, it's gradually increasing its velocity as it comes down. And he wants to be quick because he wants to catch the mouse before it hides underneath a rock or something. So the point is, though, it's coming down, but the lifting force is not going up. That is because it can arrange its wings and tuck them in maybe, so that it reduces the lifting force. The point is that just because I have a velocity term here, doesn't mean my lifting force is going to be directly related to velocity. Okay, that's why you have this equal, smaller and equal sign. In other words, it means that in the maximum possible sense, if you want to get the maximum lifting force for a particular velocity, that would be where you have the equal. That would be uv squared. Now, of course, any flying bird or a mammal like bat or anything, any kind of insect, naturally over millennia of evolution, they know what to do. I mean, they have been trained to do this, right? So it moves up and down, controls all of this without even thinking twice. So now, I want you to understand the maximum lifting force, therefore, for a particular velocity, this bat can get is this much. That's where you have the equal sign. If it is anything less than that for that particular velocity, that would be less. And that's why I have all the others less. And of course, you need to control this. You cannot have a very high lifting force all the time, because birds, insects, everything comes down and go up depending on what they're doing, right? So, that being said, let's focus on our problem. So now, we are given that this bat is going around, or rather flying around this circle. Now of course, when it takes the circle, it has to bank. So in other words, it banks with an angle. And now the lifting force, if it's moving straight this way, if it's flat, then it's always going to point upwards. Now it's banking, therefore the lifting force is going to be pointing like this. Okay. You have seen this. You have seen this a million times. If you notice this, that's a different story. When you look at all these flocks of birds, you know, in National Geographic or any other nature program, or movies, even airplanes, when they turn, they always bank. They always have to bank. Now, reason being is this: whenever something goes through a circular motion, you need to have a force that pulls it towards the center. This force is called the centripetal force. Okay? Without a centripetal force, nothing will move in a circle. Think about this. Newton's law says that, first law, if a body stays at rest without an applied force, it will remain at rest. If a body travels at a constant velocity, in other words, on a line with a constant velocity, then it will remain at that state. In other words, it will keep on moving at constant velocity unless it has an unbalanced force acting on it. Now, if you look at this bat is moving in this circle. Every moment it's turning its direction. So in other words, the direction is changing. So if the direction is changing, guess what? It is changing its velocity. Now I'm assuming the magnitude of its motion. So in other words, the speed around this circle is going to stay the same. I don't know what it is, but I'm going to assume that it's going to stay the same. So even with the speed remaining the same, since the direction is changing, we have a change in velocity. Velocity does not stay constant. So in order to have a change in velocity from f equals ma, which means you have an acceleration. Acceleration requires you have an unbalanced force on it. And this particular case, the unbalanced force is going to be given to the back by a component of the lifting force. Now let's assume for a moment this is my y direction, this is my x direction. Now mind you, this is not our regular x. Now you have to think in terms of a plane. Now this is a circle. It's circular motion. So in other words, the battery is trying to go around this circle. So my x is pointing always towards the center of this circle. Okay, keep that in mind. This is not regular x direction. This is pointing towards the center of this circle. Okay, so if I were to kind of put the weights and the forces acting, in other words, the forces acting on this bat, I always will have my weight. I cannot avoid that. And of course, let's put an angle. Now this angle is what we are going to call the banking angle. Okay. So now I said that in order for this thing to move in a circle, you absolutely have to have a centripetal force. Now that centripetal force is given to this bat by a component of the lifting force. Now that can only be done if it turns like this. Otherwise, this force cannot make a component going towards the center. So what would be the component in this case? That's exactly right. This is FL sine theta. And what would be the component going up? FL cos theta. Now, this is a common phenomenon. You cannot avoid it. So think about, for example, the story where you have David and Goliath in the Old Testament. Right? You have a David which has this stone attached to a string, pretty much, maybe a rope, and then he turns it, spins it around, and then let it go, goes and hits Goliath, and Goliath falls down, and of course the victory is to David, right? So the point that I want to make is this. In order for David to rotate his, piece of rock, let's say, it needs to be attached with a rope or a string, a strong string, we don't know, but something that holds it and makes it go around. The tension of the string provides the centripetal force. So in other words, if you look from the top, this is my piece of stone. In order for it to move around, it always should be pulled by a centripetal force. Otherwise, it will never go around this. And you know that if you were to, by mistake, to break the string, it will start going in a straight line. Okay. So my point is that this has to be there. This has to be there in order for us to have this bat to move in a circle. Now, the other thing is that this bat moves in this circle continuously, so it does not move upward or downward. Right? Now, problem, we assume that it moves in this circle, It's a flat circle like this. So it does not move up or down. In other words, vertically speaking, would the forces be balanced or not? Yes. Yes, because it will not move up or down. Okay? If it's moving up or down, that means it's accelerating, in other words, changing velocity. So if it's changing velocity up or down, guess what? That means you have an acceleration, that means you have an unbalanced force. Now this guy, he's not moving up and down. So in other words, the forces up and down, they're balanced. Right? So the first question that we need to find is this. We need to find the minimum velocity for this bat to move and fly. In other words, stay afloat. Okay, minimum velocity. So let's look at this. So if I were to say that it still moves in a circle, let's assume that, and let's try to write our formulas according to that. So the bat does not move up or down. Means that sigma Fy, all forces in y direction, are basically equals to 0. Now let's start writing our forces in y direction. Tell me a force in positive y. What would be a force acting in positive y on the bat's body? Fl cos theta. And tell me another force acting on y direction. Lg. And is it going to be positive or negative? Negative. And that would be sum to 0. So that would give me Fl cos theta equals mg. Now the bat is trying with the minimum possible velocity. It's not flying fast. It's the possible, we are trying to find the minimal possible velocity. Now, I said that this is related to, lifting force is related to velocity. Now, even though bat is trying to get the maximum lift at a particular velocity, if the velocity is small, the lift is going to be small. You can't stop it. Right? The velocity is small, lift is going to be small. So, in this case, at that particular velocity, what we want to do is we want to get the maximum lift from that velocity. The velocity is very low. And of course, it has to be the minimum possible velocity for this guy to fly, right? So, but in order to fly, these forces have to be balanced, and the minimal velocity is what we are looking for. But at that minimal velocity, maximum lift is what we want, because, like I said, it can tug the wings in, and then it would never get any lifting force, or at least it would get a minimal lifting force. We don't want that. This, bat doesn't want that. It wants to fly slow, but it wants to get the maximum lifts to stay afloat, right? So now, in order to do that, we need to maximize our lifting force, and also we need to maximize everything on this side. This is the force component in the y direction. We need to maximize all the forces in positive y direction so that we minimally equate that to the weight. Because if we can equate that, it will sustain the flight. If not, it will come down. So, one thing we have to remember is the velocity is the minimal velocity. So, everything we are trying to maximize while keeping the velocity minimum. So I'm going to say this cos theta is also going to be a maximum value. And that would be G. Okay? Now because there's two variables here. We have the lifting force that depends on the velocity. And of course we assume that this is going on this circle, and because of that motion we get this cos component that's working upward. So we are trying to maximize the effect when it's going at this minimal velocity. So if I have the maximum lifting, then I can write this formula. So that would give me CV squared instead of this. Now I can write this, but with the minimal velocity. Okay? So now cos theta, it's a cosine of an angle. Now if I write, let's say cosine with the angle, I'm going to give you 3 examples. I'm not going to go into the whole lot of numbers here. So let's say cosine, should change this. Theta is 0. Let's find the cosine, excuse me. Theta is, let's say pi, let's rather than pi, let's put degrees in theta 0 and then this. And if you calculate this, this is going to be 0.7 1 something, and this is going to be 0. This is going to be 1. This is going to be 0. Okay? Because this comes to 1 over root 2. 2 divided root 2 divided by 2. That is 1.414 divided by 2. That would give me 0.7. 0.7, that would give me 0.71. Right? So calculate this in your calculator, and what you will get is basically 1 and 0 as the maximum and the minimum. When we look at this, for any angle, because I am going through all the possible angles, middle, the biggest, the smallest, and I get the maximum at the smallest angle, minimum at the highest angle. So the maximum cosine theta is therefore is what? For any angle? 1. What would be the corresponding angle for that? 0. So in other words, cos theta max is equal to 1, and the theta for this would be 0. Right? So let's understand this. What is the meaning of this? What is the physical meaning of this? Now look at this banking angle. So in other words, this is flying like this, right? So if my banking angle goes to 0, what does it mean? It means that I'm gradually coming like this. Right? Think about this. Right? So what is the meaning? It means that in order to fly and still have a lift enough to balance this, maximal lift is only possible when it's flying straight. In other words, not with a banking angle, just flying straight. It makes sense. Look at this. If you look at this, this is a component of the lifting force. As long as you have an angle like this, you can only get a component of the lifting force working towards vertically up. If you come and make your banking angle 0, in other words, you are flying like this, and all of your lifting force is working upwards and balancing your weight. And when you are flying at a very low velocity, in other words, let's say for argument's sake, speed in this particular case at least, your lifting force is already low. And if you bank, then guess what? Only a fraction of that lifting force will come and help you to stay up. But you don't have that choice because your lifting force is already low. That means you don't have a choice but to flatten yourself up, and then all of your lifting force will counteract the weight. Then you're okay. Barely okay. Barely okay. Okay? So, now, how do we solve this? All we need to do is now V minimum is equal to mg divided by c, and I want to take the square root. Now, I've done a few steps straight together. Let's do it like this. 1 times CV squared minimum doesn't make any difference. I'm going to keep minimum right here and divide everything, and then I have mg, and then I have c, and then the square root. Now, have you seen this in real world? Think about this. In this formula, of course I'm going to let you plug in the numbers. What is the mass of this bat? Mass is given to us, right? What is the mass? 0.031 kilograms, 31 grams, right? You have the acceleration of gravity, of course, and you have the c. C is this, right? Plug in the numbers, you can calculate V minimum, but that's not what I want to really talk about for a second. Now, if you look at this, this is the minimum velocity this bat can travel. If this velocity is less than whatever we calculate, guess what? It's going to go down. What is the number, by the way? Anybody? Anybody? Put the numbers into your calculator and find me a velocity. 60.9. You need to take the square root. Almost there. Almost. 4.1. Okay. Now, let's look at this again. Means that this bat, if it were to fly with a speed anything less than this, it will not fly. It's a grounded bat. It's not going to fly. And worse, let's say for one reason or the other, this bat can only fly at this speed. It can never turn. Because as soon as you try to turn, you have a banking angle. And that means your lifting force is going to be split as a fraction of it working vertically up. And that would never sustain the weight. It will come down. So the only way for it to fly is to make sure that it flies a little bit, at least a little bit higher than this. Then only it can turn. You see the complications here. Now the other thing is this. Think about all these big passenger aircrafts. These are humongous, right? Boeing 747, all these huge planes. So therefore the mass is extremely high, right? So, and of course, they cannot, they are, in other words, in such, aircrafts, they cannot bank that hard. In other words, unless of course watching a movie, in movies they do all kinds of crazy stuff, right? Not real physics. I mean, think about it. Can Superman fly? Unless you have a jetpack attached somewhere. It just doesn't make any sense, right? So, I mean, of course, in TV and all the movies, they can show, 747s going with the banking angle really, really high. In reality, if you are doing this and sustaining a circle like this at a particular velocity, it's going to be very hard because most of the commercial aircraft, they travel at about 700 to 800 miles per hour. This is the general speed. So at that particular speeds, it's going to be very hard to have very sharp banking angles. You cannot sustain. If you go and increase the banking angle, guess what happens? The lifting force, the fraction of the lifting force or the component of the lifting force is going to be less. And the weight will overcome that, and then the plane will come down. It will never stay in a plane. It has to come down. On the other hand, think about military aircrafts like F-22, right? So they can travel at very high speeds. So that means that you can increase this velocity, and therefore you will have a very high lifting force. So the lifting force depends on the velocity. Since it can go at very high speeds, it can always have this. And also the mass is low. Mass is low means that the weight that's pulling down is low. So that means it can bank it very, very high angles and bank it in a plane. So in other words, it will never drop. It can bank it. Okay? So these things, although this is a simple problem, they are connected. Lifting force depends on the velocity. If something can go at very high velocities, then you're okay. But usually this is not the case, right? Now, let's look at this. Now, second part. What do you have?
I have a question.
Yep.
I came in late, but I don't know what that formula is. F sub L is equal to CV squared. Like, how did you, what is that?
Problem number 73.
Yeah, I'm on it, but where did you get that formula?
It's given to you.
It's given.
I know that was given to you, but how did you know?
C is my constant.
Oh, you're just
I'm going to take that
thing.
whole thing as a constant.
Okay.
Yeah, this is because it makes my life easier, let's be honest, because I have to write all of these otherwise.
Okay.
It's just my C.
So it's just like a variable is what you're...
V is my variable, C is a
These are constant that you're saying. Okay.
So I'm keeping the formula as it is, I'm just shortening for easier, management. Let's put it that way. Okay? So let's see, the second part. Assume now this particular bat can make a maximum velocity of 10 meters per second, right? That was what's given to us. So now the bat can move with a velocity that is 10 meters per second. Now, when I say that, this can be extended into aircrafts, it's not strictly true because they are much more complex. They have capacity to increase the velocity by increasing the thrust all the time, because the engines have much more flexibility, but they are also in a certain sense similar, the way they behave, because the lift always comes because it's moving. If an aircraft is not moving, most of the aircrafts, unlike helicopters, of course helicopters don't need this, but aircrafts do need to move, otherwise it will never generate lift. Lift is coming because of the wings. So that is important to know. Now, so we have a velocity that is given to us. So this bat is now moving at a velocity is equal to 10 meters per second. Right? Question is this. Now, if it's moving at 10 meters per second, it's obviously above the minimum possible velocity. So that means it can now bank. Earlier, if it was flying at a velocity 4.1, it can never bank because it will come down. So now it can bank. Now our question is, we are looking again at the vertical forces. Now, what we want to do is we want to find the maximum possible banking angle that you can get for this particular velocity, in other words, for this particular bat, right? So in other words, it's going to turn at a maximum velocity, 10 meters per second, and with that velocity, how much of a banking angle will it be able to get? Now, as you increase the banking angle, remember, your component, lifting force component acting on the vertical direction gradually decrease. Okay? So, in order for it to fly, the best way to do it would be to go with a lower banking angle. But if it's going to bank harder, that means more of its lifting force will work towards centripetal force. In other words, trying to move it in the circle rather than trying to keep it up. So as it tries harder, what's going to happen is there will be a point that the component will not balance the weight or will not be able to counteract the weight and it will come down. We don't want that. We want to come to a point where it's basically exactly balances the weight. This is what we are trying to find. Okay? This guy is still trying to fly on a plane, so it's not moving up and down. So we have a force Fy is equal to 0. Okay? So now we are going to write the same formula. So we have the total force going up, or the lifting force going up, cos theta, subtracted by mg, which is equal to 0. That means Fl cos theta equals mg. Now, of course, Fl is going to be the maximum lifting force for that velocity because it wants to get the maximum lifting force. Now remember, again, the bat can control the wings. As it controls the wings, it can reduce the lifting force to the lower end of this, because remember, this is less than or equal to sign. So in other words, it can be less than this, so it can lower this, or it can increase it up to an equivalent of this. This is the maximum it can get. So now it's going with a maximum possible backing angle. It wants to sustain that by getting the maximum possible lifting force for that 10 meters per second velocity. Okay? So now again we are going to max out the things. Now in this case though, this is an angle that corresponds to the maximum lifting force, which we will be able to calculate from the velocity given. So there is a fixed angle, not 0. There is a fixed angle that it can get with this maximum. Okay? So again, which is equal to mg. Okay? Earlier, we had no idea what is